Hello everyone, my name is Satyavitapsi and I am a PhD scholar here in IIT Bombay. This is the tutorial session, ninth tutorial session on for the NPTEL course that is Market Basic to Advanced Technologies, whose instructors are Professor N.P. Padesar and Professor Premlata Janamya. This is ninth tutorial session. Uh, this is important for solving your ninth NPTEL quizzes. So before starting, okay, let's start the session. First, I am dealing with this flow of this tutorial session will be such that it will be the single phase inverter based control, then PV based system, then we will go to some the wind based management system, and then BMS battery management system, then EV part some portions are there, and lastly we will cover this control architectures of this AC and DC microgrid and the hybrid microgrids. Okay, so starting with this AC, this is single phase inverter and this control architecture. So as you can see this that is a L filtered solar inverter with DQ current control. Why this is L filter? If you see that this is actually conversion from this is a portion of this DC system. This is converted using this voltage source inverter to the AC part, then using this filter, which is filter out to making this smooth current which is in aligned with this grid voltage and frequency. And through this point of common coupling, if you see there is a one PLL. PLL is such that that is a phase lock loop. That is PLL is full form is phase lock loop, and this is important for generating a synchronized voltage and control signal. So if you see that the point of common coupling, the Vs is taken into account, that is source voltage, and it is a three-phase voltage, then it is fed to this PLL. After that you get a theta value which is synchronized angle with this voltage, and after that this is being used for ABC to DQ conversion or DQ to ABC conversion. Okay, so if you see this L filter is there. You can use this. Many architectures are there, such as L filter, LC filter, LCL filter, LLC filter. Kind of many architectures are there. Based upon the utility, the filter had been designed. And after this, if you see this current from the input side, input means from this inverter to feeding to this inverter I. Then ABC current is taken into account. That is converted into ID and IQ. Then that ID and IQ being used to feed this control this DC and the VDC and IPV from this PV plant, and then MPPT is utilized for operating this VT, getting this VD star. After that, this ID and IQ value is being controlled using this PI based controller. Okay, then VSD and VSQ is the same, this VS and VQ value which is being taken from the source value voltages and from this grid side, and theta value which is from the PLL. Then this signal, this PWM signal is generated which is fed to this three-phase VSI for generating PWM signal. The basic crux of this utilization of this circuit is such that you have to convert from DC, which is generated from this PV side, to this AC side using this synchronized voltage, because in the AC side, if you see, you have AC voltages, that is the VA, VB and VC, which is 120-degree phase shifted, and it have certain omega t which is being constant. And also you can see that for that you need certain mechanism so that you can generate from DC to AC, and you by using this omega t, that is same for feeding to this grid. So grid synchronization loop is very important for sending this power from this AC side to the DC side. So coming back to the first part of this question, if you see, let me read the question for you. This is the considering a photovoltaic system designed to generate electricity with a maximum power point of 10 kilowatt peak. The system operates at a nominal DC voltage of 600 volt. For the design of this PV inverter, the following specifications are given. That is, the inverter must have maximum DC input voltage of the 800 volt. Inverter efficiency is expected to be 97%, and the inverter should be able to handle both grid-tied inverter and the isolated operation with a battery storage. So it means that you have a DC input from this PV side. From the PV side, you have a DC power. Using some voltage source inverter, it is fed to this AC, and which is feeding directly to this AC side. And it can operate in both islander situation and this grid connected. So for conversion this, it have a certain voltage range which is being utilized, because the what is the unit of this power conversion? That is the power which is output from this PV plant is defined in terms of kilowatt hour peak. This I will explain you further in the later slides. So what is saying that it is a nominal, this is nominal voltage which is actually being operated, that is 6 volt 100 volt, but it can operate max to the 800 volt. Why? Because the DC bus bar which is connecting with this DC side to AC side, this voltage is being should be maintained for conversion to the AC side, which is mainly 650 to 800 volts for getting this three-phase supply, that is a magnitude of 230 volt phase and 50 hertz. And so this voltage should be maintained, and maximum how much it can go, it can go to the 800 volt. Okay, so the first question is saying that what is the maximum DC input current that the PV inverter must handle. So I'm giving 2 minutes to solve this question. So please try this question. Okay, if you have any doubt, you can let me know in the comment box, or you can open your mic and ask me. Question is asking that the maximum DC input current that the PV inverter must handle. This should be at a this DC bus bar after this DC voltage, DC link voltage. Ask for a minute. Anybody? But try. Okay, let me explain you this question further. As you can see that the what is asking in the question is the DC input current that the PV inverter must handle. So what I have told you, let me explain you again. I will explain that you have a one PV which generate one DC power, then you have a DC link capacitor which have to maintain a certain voltage from between 650 to 800 volt for generating three-phase supply of 230 volt and 50 volt. Okay, this amount of DC link voltage you must need. After that, you have a voltage source inverter which convert this DC power to AC, and in between AC you have a certain filters. Suppose you may have some L filter or LC filter or LCL filter. After that you have this three-phase synchronized voltage source which is being generated. Okay, so and also in between this voltage which is being at a VG terminal, voltage this grid side terminal, it is being taken into account with this PLL to generate a synchronized voltage angle, that is theta. Then it is being used for controlling this input side current, that is the I which is generated by this VSI, then this voltage. Okay, so this is done into this DQ frame. So what I'm saying in this question is that it is the maximum DC input current that the PV inverter must handle. So in between the voltage source inverter and the PV, you have a DC bus bar. Okay. What I'm saying that it have a maximum voltage of 800 volt, which can be applied, and the power max which is generated from this PV terminal is 10 kilowatt hour peak. Okay. So what will be the maximum DC current it can inject into the inverter? That is IDC is equal to 10 to the power 4 divided by 800. That will come out to be 12.5 amps. Okay, that is simple question. What I am saying is the maximum DC current that the PTV inverter must handle. So this is a design problem, that how much current it should handle. You can also say that this some of the current will go into the DC capacitor also. Yeah, that's fine, but it is very low because the IC is omega C phase V phase, and C phase value is nearly in the microfarad. Suppose it have 10 microfarad or 100 microfarad range is there, so it will become very low. So coming to this second problem, in this question you have to tell me that for this same statement based question is there, it's the second part of that same question, that the maximum AC output power of the inverter in the grid tied operation. Okay, it is operating in the grid tied operation, maintaining this voltage and the frequency and the theta as a constant variable constant, and you have to tell me that the what the maximum AC power that inverter must deliver. Okay, can deliver based upon this question. I'm giving you 1 minute to solve this question. Just read the statements, you will get the point, what I trying to say. Okay. If you are not understanding anything, just let me know. I will help you with that particular problem. It's a very simple question. You just have to use certain factors. Last 10 seconds if anybody. Anybody who is trying, you can write in the chat box. Yes. Okay, let me give you some glimpse of it. Here, after reading this second statement, if you see this efficiency, this converter efficiency is given. Okay, you already know that if there are certain series connected systems are there. Suppose this is series connection system 1, and it is getting certain input. Then you have a series connected system 2, then 3, and multiple. So what happened to the final value? that is the output is there. So certain efficiencies are involved in the all stages in neta 1, neta 2 and neta 3. For getting the output, this neta net, what is the neta net? That is the neta 1 multiplies by neta 2 multiplied by neta 3. So what will be the output? Output will be is equal to input times of multiplied by this efficiency net. Okay, same formula you have to use here. There the only single system, that is the single stage conversion is there from this DC side to the AC side. So one efficiency is given, that is the 0.97. So P out is equal to P input multiplied by efficiency, that is equal to 0.97 multiplied by what will be the P input, that is 10 to the power 4, that is max power which can be generated. Okay, so it will come out to be 9.7 kilowatt. Okay, so if you have any doubt, you can just let me know in the chat box, or you can open your mic also. Okay, this is the third part of the same question. I request to solve this question. Okay, you got the point of this DC voltage, how to find out the maximum IDC current the inverter can handle. Second, you also got the point that what will be the P out in the AC side. Okay, third, you have to tell me that in the islanding operation in this question, how much energy capacity is needed for this power battery storage. Okay, this is a very simple question. You have, please try this question. Shiv, Devendra, Shibna, anybody, please try this question. Okay. In case of any doubt, you can just let me know in the chat box, and you can open your mic. You have last 20 seconds to solve. If you're trying, you let me know in the chat box. You can write yes, I'm trying as well, so that I can wait for some few seconds. Okay. Any answer? Shiv, Devendra, Shivna, Anthony, anybody? Okay, let me solve this question for you. Uh, but you need to try these questions here because it is very, very important for the perspective of their academics and the research, anything. So, what is the concept of this question is that in the grid connected mode, when the power generation, PV generation is low, suppose you have a certain PV here, and after that you have certain inverter, and you have a certain, you have grid, and at that particular point you have a load also. Okay, so setting of inverter and the such that when the PV is there, you should supply the load to this power by for reducing this burden on this grid, for reducing the burden on the grid. So if the PV is not there, this load should take the power from the grid. So there are certain priority based systems are there. So if the in a grid connected mode, grid connected PV generation is there. So first operation will be PV should give the power to the load. Okay. So if you disconnect this grid, it is an islanded mode of operation. If the grid is not connected, so when the PV generation is low, who is going to supply this power to the load? Okay, there is no actually energy storage concept I have implanted in this architecture. So I need to design a battery energy storage system such that when the PV is not there, then battery energy storage should supply this power to the load in the islanded operation. Okay, and also it says that when the PV is more, then it also supply, then this battery storage should charge when the PV is available, and then it's also give the power to the load. Okay, so here in the question it is asking that the capacity of the battery storage system that is required for the islanded operation of the 6 hours, 6 hours, and assuming that the average power consumption during the islanded operation is the 5 kilowatt. Okay, so there are two situations. First situation is such that when the PV is available, okay, and second situation is such that when the PV is not available, okay. So how you will design? Uh, You have to, for the designing consideration, you have to take the worst case scenario. Worst case scenario. So worst case scenario says that when the PV is not there, PV is not there, it means that how much energy capacity you have to supply from the battery. So that is actually average power consumption, that is the 5 kilowatt hour, kilowatt multiplied by the 6 hour, that is the very simple, that is 6 watt hour capacity of the battery you need. Okay, that is C option. Okay, that is the same concept. There are multiple concepts are in there when the islander situation is there, when the PV based system are there. You must have certain control architectures are there when to which supplies would be operated. Okay, and the time of operation is also there. Okay, so coming to this single stage inverter and the control architecture, if you see in this figure, I have given one characteristic, that is the I versus V characteristic. This I have explained in the previous lectures, tutorial sessions also. If you see the I versus V characteristic, the I and V characteristic is like that. It is moved from ISC, then will drop down after reaching this VOC. And if you see the P and V characteristic, it increases to certain value and it reaches to the maximum power point, then it after that it got reduces. So what is the actual operating point which we needed to operate? That is the P max level. Okay, P max level. This is done by using certain control algorithms such as MPPT control algorithm. There are multiple algorithms are there such as PNO method. Second is the INC method, incremental conductance method, and people are using decision tree based methods also, and ANN also for that. Okay, so there are multiple control architecture which can be utilized for tracking this maximum power. Okay, so if you see that this P reaches to a certain value and after that it reduces. Why it is reduces? Because the current moving from this IMP point, getting reduced. Okay, so there is a one concept of this fill factor, that is actually VMP IMP divided by, sorry, that is the VOC ISC divided by VMP and IMP. Okay, and fill factor is needed to be always greater than 1. And second point is that if you see that VOC, relation between VOC and VMP and ISC and VIMP. Okay, so IMP is less than ISC in the situation which we have, and also this VMP is less than VOC. This is actually the property, because you cannot utilize the 100% of this converters due to the certain time lag and also the efficiency of the converter. So it is always IMP is less than this VMP and VOC, and fill factor is generally you needed to be 1, but it is always uh, uh, less than or nearly equal to that, but not exactly equal to that one. Okay, so there are, in the right side image I also have shown that the variation of the current and voltage with respect to irradiance. So what happens that when the designing consideration are taking, so if irradiance, suppose I am taking neta as a irradiance, there are 1000 omega watt per meter square, it is the unit. Suppose this is maximum, and neta minimum is the suppose I am taking as a generation as 20 watt per meter square for the designing consideration, because the for the designing consideration you have to take the max and the min. And the when the manufacturer uses this concept that how they to design this, so they uses this VOC concept, that the VMP concept, that the in the 1000 irradiance, suppose you have a 10 panels with a 10 voltage of this VMP. So 10 multiplied by 10, that is the 100 volt when it is connected in series. So at a 1000 irradiance, okay, and the current is also based upon the what is the power max it has been given divided by VMP, okay. So design consideration is such that when the neta minimum is there, that is irradiance, minimum irradiance is there, at that particular point also you will get this 0.95%, that is 95% of this VMP. That is actually 0.95 multiplied by 100, that is 95. But the current is will be very very low, because the current is a direct proportional with this irradiance. When the irradiance increases, the current will increase, but the voltage will not be affected at that particular point. In the worst case scenario also, you will get the 95% of the voltage if the series connected systems are there, okay. So this is the main property with utilizing and modeling or making these panels and all, okay. So this is actually in the right side image, if you see one algorithms I have shown, that is actually the PNO method, that the perturb and the observation method. Let me explain you this algorithm because it is also important. Suppose you have this PV characteristic, that is the P versus V characteristic is there. So there are certain points which you can lie. Suppose you are at a point A and you are moving towards the point A1 and moving towards the point A2. In this situation, if you see that if you move in the forward direction, this delta P, that is the P at A2 minus P A1 should be greater than 0, and the delta V, if you see there, voltage at the point A1 and voltage at the point A2, that is the VA2 minus VA1 is greater than 0. So certain logic should be operated in such a way that D plus delta D, that is the duty cycle which is being given to this PWM signal, that is the IGBT or certain switches. So it should operate and change this duty cycle, okay. Same concept when you operating moving in the reverse direction. If you are moving in reverse direction, it means that DA2 minus PA2 minus PA1 should be less than 0 and VA2 minus VA1 is less than 0, okay. So in this case you have to D minus delta D to move in the forward direction, making the duty cycle to little bit reduce, okay. So if you see in this algorithm itself, it is monitoring this Vk and Ik, then it is multiplying this power, that is the Vk and Ik, then calculating the change in the power and the change in voltage. Then algorithm says that it is if the logic is operating, then you should go on DV logic, and based upon that you should change the duty cycle of the switch, okay. So this is the PNO method, and based upon this is this duty cycle is given to this T2 transistor or transistor, that is MOSFET or IGBT can be there, okay. So this is the main crux of this actually discussion. And what we do in this lab also, we uses certain mechanism. Suppose we have this PV emulator is there in my laboratory, that we don't have this PV panels and all, so we emulate that. There are two things are there, simulator and the emulator. Emulator is actually means getting the exact characteristic after this and with the time synchronization is there, and the PV emulator is there. After that we fitted this I, V, E radiance values and this what amount of VMP and IMP, it gives certain characteristic, and for our experimental purpose we use that characteristic which is given by this emulator using certain IO ports, IO digital or IO analog port, whatever we wanted to utilize based upon that, okay. Let me explain you further with this. this sensing and the PWM outputs. That is very, very important for if you are wanted to and go in the research field, how to actually we simulate the things in this real digital simulators, real-time digital simulators. So if you see in this left side figure, we have a certain stages, such as that we have actual system, power stages, electrical motor and drive, and the EV stage. Okay. So there are one real-time simulator which is actually used for research purpose, that is the Opel RT. So suppose you have a large amount of system which you cannot physically operate, or you cannot see the changes which can do in the physical world. So you always simulate that in a certain simulator such as a MATLAB or any other and other softwares, and then you try to match it with the real-time environment using this certain real-time simulator, that is Opel RT, and try to see the changes in the physical system that is the same as a physical system, but you are operating in real-time simulator, and what is operating should be done when you want to mitigate certain faults or any other abnormality happens in your system. Okay. So in the Opel RT itself, if you see that there are two kinds of system, that is HIL and the PHIL. Okay. So in the HIL, you can just take this, suppose you have a certain controller is there, and controller is fitted into this HIL. Let me explain you with the example. Suppose you have a DC which is generated from the PV. Okay. That is not the actual environment. You have a certain PV emulator from where you are taking this PV and data, that is voltage and current data. Okay. Then you are feeding to this certain controller is such that this is a MPPT controller, and you want to track this power and V characteristic to reach as a P max value. Okay. So what we will do, we actually implant this MPPT algorithm in certain controlling such as ICs and other modules itself. Suppose I am using Arduino, that is simple controller, that is the Arduino for this purpose MPPT tracking. Then I am giving this again from the Arduino I am getting this IO, this output of digital signal, because it is a PWM signal of 0 to 1 to on and off when the switch is happening, given feeding again to this PV emulator. Based upon that characteristic, I am getting this P max. Okay. So I'm not having a physical system, but my controller is outside of this environment. Okay. So this is the point of this HIL simulation. We are doing a closed loop simulation. Why? We are getting the power, voltage and current data. Then I am feeding to this PV MPPT algorithm which is there in the Arduino. Then I am taking this PWM signal and feeding directly to this PV emulator or the Opel RT where we want to utilize that values. Okay. So this is a kind of closed loop environment where we doing this testing. Okay. So different between the PHIL and HIL, we have a certain power amplifier in between. Power amplifier in what sense? Because if you are taking the power, because in the simulator you have the power at a very, very low level. Suppose you want to install one inverter also. Okay. So inverter will give this certain power, this AC power, which is of 230 volt. How to modulate that? You have a certain, suppose you have a 10 kilowatt of power. So how you are going to give this power to this real-time simulator? So you have to reduce this power. Then after that you can feed to this real-time simulator. Okay, which is handle this 12 volt supply. Okay. And same with this happens also when you are trying to feed, give certain power from here real-time simulator to this power inverter. Okay. It is also a low level. Suppose you are bidirectional inverter is there and you want to send from the 12 volt to 230 volt signal. So how you will do? So this power amplifier will increase the voltage level which is already there, this 12 volt to 230 volt. Okay. Same things you can do with this EV drives, MOSFETs and other kinds of simulator, inverters and battery emulators. Same kind of things. If you see in the right side figure, in the upper portion, I have shown you one Opel RT simulator. You have one host PC is there where the MATLAB platform is there, where you implant your codes or model, which you have model for this real-time behavior, seeing this real-time behavior, and you have a certain IO ports. IO ports is such that suppose you have an Arduino which takes the signal analog and gives the power to power digital, okay, and the controller is inside of this Arduino board, okay. So what you will do, you will run this model in the MATLAB and take this analog signal from this IO ports, directly feed to this Arduino board, and take the digital output and feed to these channels. Okay, you have a certain sections such as this is the input, analog output, and the digital input, digital output ports are there. Suppose six here, you can see that there are 460 32 ports are there. Okay, so based upon that, you can use this real-time simulation and the closed loop algorithm, CHIL or HIL kind of things. Okay. So in the lower portion, if you see, I am sensing the AC voltage, AC current, DC voltage and current, and then feeding to this Opel RT input IO port, then taking the control loop in the RT lab to the MATLAB and assembling. Then I am generating again the digital output port, sending this power through the digital IO port and the PWM signal, and then we are generating the RYB signals, and it take the power of this 12 volt supply. Okay. So this is a kind of real-time simulation which we do in the laboratories also, which is also demonstrated in this NPTEL videos also. And there are two types of architecture actually with this solar inverter, that is the single stage solar inverter and dual stage solar inverter. In the single stage, if you see that there are direct connection of this PV panel to DC to AC converter, that is actually inverter through the DC link, and you have after that you are connected to the AC. But that is not same case with this dual stage inverter. You have certain DC to DC converter is there, and after that it is feeding to this inverter. Okay, in between you have this DC to DC converter. Okay, suppose you have a PV panels which is not generating this 650 to what I have told you, 650 to 800 volt, then you will get certain current harmonics which is not desirable during this operation. So if the voltage level is lower, suppose you are generating 500 volt, and so the current harmonics will be very high. So what you will do, you will enhance the voltage from the 500 volt to the 650 volt, then you send this power to this inverter. Okay, so one stage of DC converter will be there when the voltage is lower values, which is not applicable for generating sinusoidal signal, which is of 230 volt and 50 hertz. Okay, so if you see the control architecture of this single stage solar inverter in the left side, you have the MPPT algorithm, which is taking this VPV, which I have told in this PNO method also. It sends the take the samples of the V and I value, then fed it to this MPPT controller. Then you generate one VDC link voltage. Then through the VDC link star and one VDC link voltage which is already available. Then DC link voltage is being controlled by controlling this ID star, and QAC is taken from this DC to AC converter, that is the what amount of QAC star you want to apply. Generally we take it as 0 because the IQ we take as a 0. We don't want any reactive power being supplied because we want to utilize only active power. And if you see in the DC to AC conversion also, what is being sensed, that IAC, VAC, and using the PLL, the synchronized angle is also developed. So this is the single stage architecture. And if you go in the dual stage, what is the extra things is there? That is the DC to DC converter. And in this stage, you have to take the consideration of the DC link voltage and also the voltage which is generated from the output side of this DC link DC converter. Okay, so there are means increased amount of this control architecture is there. If you see in this also VDC link which is generated by this MPPT, and VDC link which is taken into directly to the DC link voltage control. Okay, then it generates this power and the VQAC star. In the previous, what we are generating ID star and the QAC star. Now we are taking directly this PAC star into generation consideration. Why? Because we have the actually the voltage level which we needed, that is 650 to 800 volt. But in the single stage architecture, we don't know the what the voltage would be generated. Okay. So this I have already explained that it has a one conversion state, so it efficiency is higher, but the problem of the DC link voltage maintenance will be there. And this VV panels are directly connected across the DC link. And in the dual stage, we have the two conversion stages, and the PV panels are directly connected to the DC. And conversion losses are more because you have a dual stage, and so efficiency will be lower. Okay. So coming to this wind power generation, that is the second module of this lecture. If you see that this is the what in the previous lectures, previous tutorial sessions, I have explained this what is the working principle of the DFIZ and all. So if you see that there are multiple types of wind generation plants are there. That is a type 1, type 2, type 3, type 4 are there. Okay. So in this DFIZ comes in type 3. Okay, this is DFIZ. So but you can see that DFIZ have a parallel converters are there, which is operating in synchronism with this grid, and thus variable pitch control, variable speed of this wind turbine. And in type 4 you don't have this parallel section. Parallel section is not there. Only this stage which is in the parallel section, it is directly being connected in the one stage directly to the grid. Okay, so no parallel action there in the type 4. And also the important point is the 57% penetration if the this wind power generation plants are being installed, it is type 3, and the very less are there in the type 4. Okay, and the type 1 type 2 is the one rotor bit induction generator were there, which is not being actually utilized in the present scenario. Some places are there, but we generally utilize the DFIG based system. So let's go to this brief introduction part, that is the arrangement, how the power conversion is there. So if you see that the wind velocity is there, suppose so the kinetic energy being utilized for the power conversion, and the power is directly proportional to wind velocity Q. Okay. So it is fed to the gearbox or voltage, this velocity increment kind of thing, because you know that it is directly proportional to the number of teeths which is being utilized in the gearbox. Then you have a certain generator, doubly fed or wound rotor, or any other type of generator. Then it is fed to the power conversion stages, then transformer, then to the power grid. Okay, this is the basic schematic diagram. So here I have explained the DFIG based system. Suppose if you have any doubt, you can ask me in between. Okay, there is no issue in that. So if you see that this wind velocity is there, so there is a possibility that when the wind velocity is low, so what will happen? The power which is being sent to the grid will be not as per the level. Okay, because the power is proportional to VQ. Okay, if the V is low, then power will be low. Okay, so what will happen in the DFIG based system if the power generation is low? Okay, it take the certain conversion from this power directly from the grid and maintain this power which is going through the stator as a constant. Okay, so also when the generation is very high, what it will do, it will do that extra power it will send from this power, that is the parallel path, and maintain this PS as a constant in that situation also. So this stator, that is stator power, that is actually being fed to this grid actually as a constant. Okay, so there is no variability. Why there is no variability? Because it is taking power from the grid when the generation is low. Okay, So based upon this DFIG based operation, if you have any doubt, I have explained this DFIG in the very detail, how the sub-synchronous speeds come into existence, how the power conversion is there, how the power transfer wing takes place. You can see that tutorial fourth session. Okay. So based upon that, I have one question. I put it two, three questions on that. This DFIG based system. So you have to solve this and tell me the answer. Okay. I'm giving the few minutes to read the question and the solve. Okay. This is a very simple questions. You must try. I'm giving you 3 minutes to solve this question. In case of any doubt, just raise your hand or you can open your mic and you can also write in the chat box also. That's pretty easy. You can also guess the you can also always calculate case also. That is also one of the most important thing. So do the calculated case also. In case of any doubt, just let me know. Any answers from anybody? You can do the calculated case also. No issue in that. Anybody? You can guess also. Just see A, B, C, D. Maybe. If you don't know, you can do a calculated guess. You don't know. Shiv, Devendra, Dheeraj. Any answers? Oh no, I guess C. Okay. Sivna is saying guess. C, he guessed. C guessed. Anybody? Shiv or Lavani? Any answers? It's a very simple. You just have to use some concepts, not the actual formula. Okay, formula. There is no need of formula in this question. I assure you. Okay, let me explain this question. Okay, what is saying that a wind farm is there which uses this doubly fed induction generator to generate electricity, and the rated capacity of DFIZ is 3 megawatt. Okay, and they at a wind velocity of VW at a 12 meter per second. Okay, and generator is connected to 690 50 hertz electricity grid. Okay, from the grid side, from not from the router side, it is from the grid side that 690 volt and a 50 hertz supply is being generated. Okay, and during a peak wind velocity period, the device operates at an electrical efficiency. It is saying that what is being converted from this mechanical to electrical, that is the P uh, out from out, that is the electrical, divided by P out, that is mechanical, is equal to zero point 0.9. Okay, and the router of TFIG can adjust its speed in a range of plus minus 30 degree around the synchronous speed to optimize the power. It means that speed what is being actually there, that is actually can go plus minus 30 degree. Why? Because I have told you that if the velocity is low, wind speed is low, so there is no much power generation. So what it will do, it will take the power from the grid side, from the parallel path, and feed the power to the from the rotor side. Okay, so to make the what is the power which is going, that is PS as a constant. And if the speed is higher, it will send the extra power through that parallel path by making this PS is equal to constant at that rate. So what is the question is saying? What is the slip percentage? Slip percent means percentage slip when the DFIC operates at maximum power point level. Okay. So what you know this induction based generator, that NR is equal to NS 1 minus S, and S is less than 0 during this super synchronous speed when it is operating. Okay. So but the problem here is I have not given this NS. Okay. I have given this NS. You can calculate. That is the 120 F by P. Okay, that is the NS equal to 120 multiplied by 50 divided by P. What happened? We have not given the P also, but we have also not given the NR also. What is the actual speed? So how we will calculate this S? Okay, so answer is D, because the C percentage cannot be determined from the given information, because we don't have this NR, we don't have this pole value. So how you are going to calculate this S? Okay, so correct answer is D. So there is no calculation involved. Okay, if you have any problem, you can ask me. Okay, moving to this second problem, that is important. Okay, so try this question. Same question is there, only you have to give me this approximate mechanical power. That is also very simple. You just have to use a basic equation, not which is of standard values, just formula. Use the rated capacity of the DFIZ, because the rated capacity of DFIZ is what is being generated from the DFIZ system. Okay, that is the output power, and the efficiency is also given. So you can calculate this what is the input. Just use that formula, that is the P mechanical output. P electrical output divided by P mechanical output is equal to efficiency. Maybe got my point. Okay, maybe see, either there are two situations are there. Either you are correct, either you are not correct. So there is no possibility of half true and half false. Okay, anybody else wanted to give the answer? Okay, let me explain you. What it is saying this in the question is that assuming that TFIC is operating at its rated capacity and the electrical efficiency, what is the approximate mechanical power input from the wind to the generator? Okay, so what is the main architecture is there? You have a certain wind which is connected to from this rotor side, and you have a stator which is feeding power to this transformer to the electricity grid. Okay, and from this rotor side, one more conversion path is there, that is the DC to is DC to AC to DC conversion path. Then you have a DC link capacitor. Then you have DC to AC conversion path, which is feeding to this after this, before this, in this transformer. Okay. Oh, okay, that is the same concept that so what I'm saying that there are certain efficiency involved from this mechanical side and certain efficiency from the electrical side. So efficiency is given as 0.92. That is the P electrical output divided by P mechanical input. Okay. So what is the P mechanical input? That is the P electrical, that is the rated output 3 megawatt divided by this actually 0.92. Okay, so what will the mechanical power generated? That is 3 divided by 0.92, it will come out to be 3.26. Okay, that is very simple concept, that is you have to use this efficiency formula. So this is a third question, that is the concept related to reactive power. Which load absorb reactive power? Which load deliver reactive power? The nature of the capacitor, capacitive and inductive loads. Just you have to drive this based upon this concept. What I have told. Just give wrong answer. You can give the wrong answer also. Just try. Just say that A with some logic, B with some logic, C with some logic. Okay. Just do it ideal and make some interaction. So it will be helpful for you also and me also. In case of any doubts, let me know. Use the concept of that, what I'm telling, that if there is a inductive load, it will absorb the lagging power. If there is a capacitive load is there, so it will deliver this lagging power, lagging reactive power. Okay, I got one answer. Maybe A lagging means reactive in inductive nature. Okay, anybody else want to try? one answer. That is the A, B, C, D, any answers, and just clear with some logic. Shiv, any answers? David, Dheeraj, Shivna, any answers? Just I you also try, at least you try. This is a very conceptual question, not conceptual. It's a very easy question with some logic. And okay, now clear. Now it's clear. I think the one was low. Now it's clear. My voice is clear, Lali? Okay. So we'll use this microphone. So anybody else you want to give the answer? Okay, let me explain. Okay. The answer is A, B, C, D. Let me check. Okay. So what is the question is saying that if the grid requires a power factor of 0.95 lagging for the grid stability, which of the following action is needed from the DFIG control system regarding reactive power? Okay. So it is saying that from the grid side that is a 0.95 lagging power is there. Lagging reactive power factor of 0.95 lagging. It means that it is an inductive load. Okay. It from the grid side, the inductive load is connected. So DFIG control, what it will do, it will supply that extra reactive power to this inductive load. Okay. So DFIG will supply this reactive power to the grid. That is actually correct from the other side. That if the nature of the power factor is lagging, so you will send the extra reactive power from this DFIG control, so that make this unity power factor. Okay. So that is the main concept. Okay. So that is the main concept behind this DFIG control, extra feeding reactive power from the system to maintaining this stability of this unity power factor with the load is of 0.95 lag. Okay. So let's jump to the other side. Other side in the sense कि controller, how the emulator is being actually fed and how this actually control is being done into these emulators. So if you see that what I have told that there are two sides are there. One is rotor side converter and second is the grid side converter. So in between both, what is happening, that is one DC link capacitor is there which have to maintain the voltage at a constant level. Okay. So if you see this 415 volt 50 hertz and AC supply is there, which is being converted to DC, then it is fitting to some chopper, then you have a DC motor fitted. Okay. So for generating this wind characteristic, what is being used is DC motor is being used. Okay. So based upon that, this wind characteristic being emulated. Okay. So what is the input? Input you have to give, that is the you need the wind velocity, pitch angle, that is beta, that is the AB, which fed into this wind power calculation. And then you know that this torque is equal to power by omega. So power is being divided with the omega to generate torque. And this torque is equal to, in the motor sense, you can say that this K times of motor constant and the phi and the IA. Okay. So how you generate this I reference? That is the torque divided by Km phi. That is the constant. If you divide it by, you can generate I star. And what actual motor current you need, that is being subtracted, then fed it to this PI controller. Based upon that, this duty cycle is being given. Whom it is given? Given to this three-phase chopper. That is the winds. Okay, based upon this IGBT based controller is there, which takes the input from their logic. What is actual motor being generated? Okay, so based upon that, this DFIG emulator is being worked. So coming to this two-side control, that is the rotor side control and the grid side control. If you see that the wind velocity is there, which is being fed using this MPPT reference, that is the PNO method, which I have told you, that is the same concept they use for generating this reference speed. okay, which is subtracted using this rotor speed. Then it is fed to this PI controller which generate IQ star, okay, from 0 to max value. Here 0 to max means you have to use saturation block here to fade this, maintain from certain level from 0 to V max, certain reference IQ star max. Then you fed this through this PI controller and generate VQ rotor side converter star. Okay, same with happen with the reference frequency also. Reference frequency is generated, then the estimated, then PI controller is fed, then ID star RSC generated. Then what actual you need, that actual RSC control, then fed it to this PI controller, then VD star rotor side converter is being generated. Then it is fed to some sequence generator, that is DQ to ABC converter, then fed to this PWM generator from the rotor side converter. Main concept is such that you have a stator is there, and you have a rotor, okay, and at the rotor side your wind turbine is connected, that your wind fins are connected with some controller, and the same rotor side you have a two controllers, that is the AC to DC converter, then you have a DC link, then you have then again DC to AC conversion, then feed it to this grid, okay. So what happens that this left side converter is that this is a rotor side converter and right side is the grid side converter. Here we are studying about this rotor side converter. So this DC to AC converter, that is, or AC to DC converter, bidirectional converter, it needs certain PWM pulses for this operation of these switches, which is being generated through this control of what? Control of this wind velocity, this rotor side converter, that is wind velocity and the frequency, okay, that you need know, because NR is equal to NS 1 minus S. Based upon that, NS is 120 F by P 1 minus S, that is NR. So what happens that this NR will based upon this wind velocity, how much you've been generated, and the frequency also. So these two have to be controlled. Based upon that, the operation should be taken to maintain this stator side power as a constant level, okay. Second, we can see that this is the grid side control. Grid side control, what you will need, you need this DC link voltage to be at a constant level, and second is the grid side current should be a constant level. For that, if you see that VDCM is generated, okay, then it is compared with the actual DC link voltage, then it is fed to the current reference generator ID star, then the ID which is being actually needed, then it is then fed to this PI controller, then VD star is being generated. Same with this reactive current control IQ GSC, then it is compared with the IQ GSC star, then it is fed to this PI controller, then VDQ to ABC converter is there, conversion happens, then this PWM conversion goes to the GSC side, the grid side converter, okay. So what is happening that you have a two-side converter, that is a rotor side converter, and the grid side converter. In between you have a DC link voltage. So when you are where the generation is high, that wind velocity is very high, so what you will do, you take the rotor speed at a reference and the frequency as a reference. So in the higher generation time, you will send the power from the rotor side converter to the grid side converter, then to the grid, okay. So when the generation is low, what you will do, you will take the power from the grid, then fade from the grid side converter to this rotor side converter, then you maintain the velocity to make the PS as a constant level, okay, stator side power. So there are two sides conversion, no. So from the moving from the rotor side to grid side, you have to maintain the DC link voltage also, because I have told you for feeding the power, that is 230 volt phase and the 50 Hz, the DC link should be maintained up to this 550 to 800 volt level, okay. So for after that only this 230 volt phase being generated, okay. So this voltage should also be maintained by taking the power from the grid side itself. So these are the main brief discussion of this grid side and the rotor side conversion. So let's move to our third side, third module. third module is such that we are taking this BMS kind of study. Here we will go through some of the concept, and after that we will go through the further slides that is actually related to EV. We will do the brief discussion on the electric vehicles also. So this is the BMS circuit. If you see that, in the previous tutorial session, what I have explained you that there are certain two quantities are there. One which is predicted, and one which is actually being measured. Two quantities are there. So what is the measured quantity? That is the voltage, current, and temperature. What is the predicted parameter? That is a SOC, SOH, and other online and other method. And after that, what you will do? You will predict this energy power. Okay. So these measured and the predicted quantities are being fitted in this BMS itself, where it takes the certain measurement using the sensors such as the voltage, current, and the temperature sensor. After that, it estimates the SOC and SOH using certain techniques. Then it do also balancing. Balancing, we will study that what is balancing and how many types of balancings are there. Then it will calculate the energy and this power of this battery pack. In the right side image, you also can see that further measurement happen, that is the voltage, current, and the temperature. Then the estimated, what is estimated? The SOC. Then what been estimated? Then SOH. Based upon that, battery balancing happens. Then the energy and the power limit is being calculated. Okay. So there are certain estimation methods of the SOC, SOH. SOC methods I have explained you. If you want to detail, then you can go to this fifth tutorial session. Okay. SOC, what I have told you, there are Coulomb counting method are there. Coulomb counting methods are there. Kalman filter based methods are there. I have explained this Kalman filter in the detail in that tutorial session. For this SOH estimation, there are two types of measurement can be happen. Estimation can happen. That is the direct measurement or indirect analytical method. In the direct method, you actually measure this capacity, internal resistance, and impedance. After that, you estimate this SOH. In the indirect analytical method, you fit some model such as the Kalman filter based model or the data driven model or the both, that is the data driven plus model based method. After that, you estimate this SOH. Okay, that is the very important parameter. And also there are certain research papers are there which say that when your battery capacity drop down to 10%, you should discard your battery. Certain literature also said 20%. There are certain not actual limits are there, but the manufacturer says that when the 10%, 20% this actual capacity got deteriorated, you should replace the battery. Okay, you can go for the second life cycle of the battery. So based upon that, this is the one of the question based upon this state of health. You have to tell me that which options are correct and what is the correct SOH and the what is the condition of the battery pack. Let's go through this question. Just read it once. I'm giving you 3-4 minutes to solve this question. That's a very easy question. You just use a simple formula which is already given in the question itself. Okay, A and D, two options. Are you sure? And they saying A and D. SH, maybe only one option must be correct. This is not a multiple choice question. Okay, D is correct. Okay. And you have to think something in this, that SOH, if you're saying 20%, okay, so a battery manufacturer or the EV operator, he must discharge this battery before it reaching 20%. Okay, so the EV which is being actually being operational, it should not go below this 80% SOH limit. So you have to think that the 20% limit will not exist in between. Are you getting my point? Because the up to the 80 at the 80% itself it got discarded. And I have specifically mentioned in that first statement that BMS is responsible for monitoring and managing lithium ion battery pack used in the electric vehicles. Anybody else who are trying? Sure, Devendra. You have 10 seconds more to solve this question because I have many slides to cover today. Okay, uh, let me explain you this question. What is stating in the question is that a BMS is there which is responsible for monitoring and managing the lithium ion battery pack which is used in the electric vehicles. The initial capacity of the battery pack when new is 100 ampere hour capacity was there. Okay. Then after several years of operation, a capacity test is performed on the battery pack and it is observed that the battery can now only store 80 ampere hour of the charge. Okay. Initial capacity which is old is equal to 100 Ah and new is equal to that 80 Ah. Okay. The state of health of the battery pack is calculated. That is the SOH is equal to ratio of the current capacity to the I initial capacity and the new capacity. Okay. So calculate the SOH of the battery pack and determine its condition. Okay. So through the question you can say that it is saying that SOH is a factor of this I new divided by I initial. Okay. So capacity what is being given, that is the actually current multiplied by the time. Okay. And the time in what sense? Time in the sense that it can discharge this amount of current in that amount. As per the my knowledge, SOH is at 15% or 20 years. Go to around 60%. After that, we do not. I will explain that. I multiplied by T is the actual capacity. Okay. In 1 hour, it gives this 100 ampere, and certain zero point 0.5 hours it can give 200 ampere, and there are limit also the how much discharge. Okay. So current capacity is new is 80 amps and the I initial is the 100 amps. Okay. So health is 0.8, that is the 80%. So currently the health is 80% and I have told you that when it is deteriorate below the 20%, it have to be this satisfactory level is there, but it have to be immediate replacement. That is the option B is correct. Why? Because I have told you that when it goes 10%, 10 to 20% below the rated capacity, it have to be replaced for the EV applications. Try this second question. This is also an easy question. So I will explain meanwhile I am explaining the Dharni question that as per my knowledge, SOH at 50th or 20 year, it goes to around 60%. After that, we will not use battery energy storage system. Okay, there are three concepts are there. First is what battery pack you are using inside of the vehicle. Second is what energy storage you are using for this grid applications. There are two different kinds of things out there. In the BESS, there are two types of lives. First is the cycle life. Second is the your actual what is the periodic life cycle that is there. That type of cycle when they use the charger charge the battery, that is the long time, that is the charging discharging cycle first. Second is the calendar life. When you place the energy storage system for the long time, then this aspect will deteriorate. Okay, so there are two different point of view of this battery storage. One in the EV application, second is for the grid support application. Then you are trying to say that battery energy storage system for the grid application, where this aspect in the calendar life, in the calendar life, it will deteriorate. Okay, and also the what kind of battery you are using. That is a lead acid battery or the lithium ion battery. The common knowledge that is for the EV application. If your battery capacity goes below 20%, you should discard your battery. Okay. Try this question. Uh, this is also based upon the same concept, but here one catch is there. Now my voice is clear. Okay. Try this question. This is also a very simple question based upon the same concept which we have discussed. Everybody? Well, at least we have started to move forward. Just use the concept to what I've already told you, there's SOH concept. Okay, if I get 50, maybe 90%. Okay, I got one answer. Let's move forward. So Dhardi was saying that after 15th year or a certain time duration, that is the 20th year, after that you should discard the battery. Okay, same. There are two concepts. SOS is actually the combination of two life cycle. That is the cycle aging first. Second is the calendar aging. Okay. Calendar aging is such that when you place your battery in ideal situation, you are not doing any charging or discharging. After few years, it will degrade, okay, to some percentage. Cycle aging is such that when you charge and discharge this battery for the your purpose, then it will degrade on that, and the both factors are responsible for the SOH. but the main portion what is being responsible is the cycle aging, because the battery is in working condition and you are actually actively utilizing that battery. Okay, so calendar aging will happen after few years, suppose 15 year, 20 year. Okay, but the cycle aging will happen when you use the, suppose manufacturer given the 1000 cycle you can use, you have used this 900 cycles. Okay, after that you should discard the battery when you use this 1000 cycles or less than that. That is actually based upon this temperature also, what specified temperature the manufacturer have given, that you should utilize that certain amount of life cycle. Okay, so coming to this question, that what is saying that a BMS is employed to monitor the SOH of the lithium battery pack used in EV application, and the BMS utilizes a sophisticated algorithm to estimate the SOH. And during a routine check, the BMS record that following information: that initial battery capacity when new was 50 Ah, and the when battery capacity, current battery capacity is 50 Ah, and the total lives and discharging cycle experienced by the battery is 500 cycles, and the lifespan says that 1000 cycles. Okay, that's fine, but the catch here is if you use the SOH formula, that is the ampere hour based formula, what I will already tell, 45 by 50 is equal to nearly, let me calculate, that is 45 divided by 90 is equal to 50%. Same, that is 45 divided by 50 equal to 90%. Okay, 90%. So that is the same formula which I have used, that is actually true, because here we not considering the life cycle, because the life cycle inherently being taken into the capacity fade. Okay, what I have told you that SOH have a two parameter, that is a cycle aging and the calendar aging. Okay, and this cycle aging is already being utilized, because initially the 1000 cycle being manufacturer have given, you have utilized the 500 cycles. Based upon that, your capacity has been deteriorated to 45 pH capacity. Okay, so that is actually being accounted due to this cycle aging itself. So the capacity which is already being given has already been taken, incorporated this cycle aging. Based upon that, SOH is equal to 45 by 50 is equal to 90%. Okay, that's true. If you have any doubt, you can ask me. Let's move forward. This is the reasons for the cell balancing and the cell balancing techniques I have utilized. This is a temporary and the permanent SOH, and this temporary SOC will happen due to the leakage and the self-discharge current, Coulombic efficiency, performance and operation, and uneven temperature of these cells. Okay, and the SOH, which is a permanent damage to the cells, it happens due to this internal resistance increment, that is the self-discharge, SEI, that is the static electrolyte interface formation, when the lithium ion get intercalated inside of this graphite layer, where this SEI layer formation happens, and the performance and the operation. Okay, and if the balancing is not being implemented, the weak cells or the less capacity cell tends to discharge faster than the other, and also the if it is continued, it will lead to this cell capacity cell, that is the premature replacement and all, and the in the cell capacity also get deteriorated, and the full cell capacity which is connected to the load, it will neither discharge or charge. What is actually the cell balancing? You have a certain cell capacity. Suppose you have 3s1p cells, that is the 3 series connected and 1 parallel combination. Okay, that is the meaning of 3s1p. So suppose it have a 4.2 volt voltages are there, that is the nominal voltage capacity, and but this is not actually the same, because there are temperature variations are there, improper cooling arrangements can happen there, and the memory effects are there, and the leakage are there. So this voltage cannot be actually it is not actually in practical situation are the same. So what happens that there are certain algorithm which says that if you have this 4.2 volt, if it goes 4.1 below 0.1 or go above 0.3, then the balancing should be done. Balancing in what sense? The extra, if you go from 4.2 to 4.3, it means that excess charge has been taken. So you should discharge this excess power to this 4.1 volt cell, okay, if the battery pack, so that you can maintain this 4.2 volt level for the all cells, for the actual utilization of the cells. So there are two types of balancing, that is the active balancing and the passive balancing. So before balancing, if you see that there are four cells are there, B1, B2, B3, B4, and after we do this passive balancing. In passive balancing, we dissipate the extra charge which is being there across this resistor, which is actually being in the form of heat, that is the I square or loss T. Okay, so and how it is done, it is done to a minimum level of cells. So you should calculate this, what is the minimum voltage of this voltage level of this all the battery cells, and discharge till that voltage level. And in the active cell balancing, there are one reference should be setted, and after that the extra charge being transferred to the other cells. Okay, so here the extra cell is not being, extra charge which is there in the cell is not being dissipated, it is actually being utilized to increase the voltage, this charge level of the other cells. So this is a kind of cells is the active cell balancing techniques. Okay, so based upon this architecture, I have one question. So I request you all to solve this question. This is actually related to the passive cell balancing. I need at least one answer from a different person. Shiv, Devendra, Dheeraj, SK. Okay, D answer. I got one answer, but I need from somebody else also. Devendra or Shiv or Dr. SK. At least you should write something like that, A, B, or C, something. Okay, let me explain you this question. Correct answer is A, actually. So what is saying in the question is that you have a certain battery pack for this electric bicycle, okay, and each cell have a nominal voltage of 3.6 volt, okay, and the capacity as 2.5 Ah. Okay, so battery pack is arranged in a configuration to meet the both voltage and the capacity requirement. That is true. And if the BMS is programmed to balance the cell when any cell deviate from the more than 0.05 volt from the average voltage in the pack. Okay, that is fine. And a scenario arises when the average voltage pack in the 3.65 volt and determine the voltage range within which the cell balancing would not trigger. Okay. So what is saying that there is a one nominal voltage, that is the average voltage is there, which is 3.65 volt. Okay, and also it is saying that if voltage deviate more than 0.05 volt, 0.5 volt deviate more than then the triggering will happen, this BMS program. After that only it will do this cell balancing. So there is a gap of 0.05 volt. So above 3.65 volt, above that 3.7 volt will be there. Before, after that, it can trigger this voltage. Okay. So if it can go the lower value also. If there is a 0.05, it can go to this 3.6 volt level also. So there is a band in between 3.6 to 3.7 in which this BMS balance should not do any balancing. Okay. So the what is the option is that 3.6 to 3.7, that BMS should not do the balancing, but above that, if greater than 3.7 volt or less than 3.6 volt, it start the balancing algorithm. Okay. So that is the correct answer. So let's go to this further. Actually, this okay. Then you can ask. You want to ask anything? How D is wrong? Okay, let me explain. 3.6 to 3.65 volt. Actually, that is also true. Sorry for this is also true because it is coming in the that band itself. That is the 3.6 to 3.65. That is also correct. That is also true. And the false is that is the 3.65 and this, and this can also be correct. That is the plus minus 0.05. So it will not be triggered. That is the same answer. That is the A, C, D options are also correct. That is true. Yeah, confusing is there. I think the question is not framed that much based upon that conceptuality level. So let me explain you further with this cell balancing methods. That is the passive balancing method I have told you, and the active cell balancing methods are there. Overcharge, if one method is there, shunt resistor based method is there to discharge the extra charge which is being there in the cells. And active cell balancing is such that cell to cell and cell bypass and the pack to pack. This is based upon the algorithm which is being monitoring the cell voltage or the pack voltage, and based upon that the adjacent cell to cell, any cell, and the cell direct cell to. Okay, so these are the different types of cell balancing algorithms. So if you see that in this is the one IC, this balancing module is there which connected to 3S1P battery cells, that is 3 series connected cells, and for that you have to do this balancing. So this is the CHIL hardware setup which is already been explained in this NPTEL lecture itself, that this whole methodology is being implanted this OpenLRT using MATLAB and the Simulink, and the host PC is there, and this is the IO ports, that is OpenLRT, and DSP which is connected to OpenLRT, then a signal monitoring. So what happens that this cell voltages are there which monitor the cell voltage, and this is go to this load. Suppose you have connected one resistor also for this monitoring this load, how much discharge is there, how much voltage is there. Based upon that, you transfer this signal to some place where you monitor this. Okay, and based upon that, you give the certain signal to this balancing algorithm to operate. Okay, So that is actually the CHIL hardware setup. Further moving to this, actually this block diagram of this balancing circuit, if you see, this is the 3S1P what is being there. This is the cell monitoring box, that is the CMB, CMB2, CMBM, and which is connected to this voltages, that is V1, V2 and V3. This is the driving circuit, and this is the L, and this is the one circuit, that is SOA1 switch. If you see that this is the architecture is same as this boost converter itself. Okay, so based upon that, this actually signal, this is TMS architecture is there. TMS, one of this module is there, where this PWM signal and DSP signals has been utilized for A to D conversion and other alls. So based upon that, this balancing is done. If you see that this all monitoring system, that is the inside of this Opel RT itself, and after that this charging and discharging operation is being happening based upon the algorithm which are already being installed inside of this balancing circuit. So further moving to that, this is the we are coming to this last, how is trips 6.3.6 to 3.65. Okay, I will explain you in the last this Dharni. Okay, let me explain you few things based upon this EV architecture. That is the if you see that there are certain consumers are there, and there are certain stakeholders are there in the electric vehicles. If you see the central part, this is the EV customer is there, which buy the EV from the certain OEM. Suppose there is Tata is there, Nissan is there, and other OEMs are there. It buys from there, and there is need of this chargers also. That is the for charging this EV vehicle. So private charger, public charger, charging point operator, one of the point, and for charging you they will charge certain this fee for that purpose. So there are certain payment manager is also there, electrical mobility service provider, EMSP says that suppose you are living in Mumbai and you have to travel to Jabalpur. So in between for charging this electric vehicles, if the certain chargers are for Tata is there, for that you need EMSP, that electric mobility service provider. And there are certain authorities, suppose this is Discom is the energy distributor, energy generation and storage is there, charger manufacturer are there, so the EV manufacturer are there. So there are multiple stakeholders involved in this electric vehicle supplies. Okay, from this payment gateway to manufacturer, charger providers, and the different types of this services such as the EMSP services there, infrastructure you needed, public authority, private authority. So there are multiple stakeholders are there. So coming to this types of charging infrastructure, there are certain types based upon the multiple units. Suppose there are, on the basis of the process, you have two types of charger, that is the bidirectional charger and the unidirectional charger. Bidirectional is what sense? For the V2G, for the V2H, V2V and V2B kind of things. That is the vehicle to grid for discharging the power and the sending the power to the grid. Vehicle to home, sending the power from the vehicle to the home. Vehicle to vehicle power and the vehicle to building. Okay, and the unidirectional charger is the V1G charger for just charging the vehicle. And based upon the connector type, if you see, there are AC chargers are there and the DC charging facility is there. In the AC charging, there are type 1, type 2 CCS. CCS is combined charging support, which involve the type 1 and type 2. And for the DC charging, you need the high power, that is the CHAdeMO, CCS, Tesla's superchargers are there. And based upon the power flow, if you see that there is a plug-in charger is there. If you just use the charging gun for the plugging into the vehicle and charge, and there are certain wireless charging is also there based upon the inductive and the capacitive phenomena. And other process is that swapping. When you use the battery and you go to a certain swapping station, you place the discharge cell and take the new cells which is already being charged. And based upon the use of this charging infrastructure, there are public chargers are there, private chargers are there, semi-public chargers are there. A savvy public chargers are such that the infrastructure is developed. Infrastructure is developed by certain private authority and some other third party install the charger. Suppose there is a building and you need the chargers to be installed, so the breathing premise will be handled by somebody else and the charger is being handled by somebody else. So that is a kind of semi-public charging infrastructure. And based upon this charging speed, suppose you want the fast charger, medium charger, slow charger. So based upon that, the type of the charging speed, you have a certain types of chargers. Okay. So coming to this connector types, there are various types of connectors are there, which I have told you: type 1, type 2, CCS, CHAdeMO, GBT. You will see this type 1 charger. Type 1, if you see that, this is the old type of connector is there, which is mainly utilized in the Japan and the USA. If you see that, there are certain pins are there. Suppose this is there. So when you need a charging, when you install the charging infrastructure, suppose this is the EV. EV is there. For charging, you need the charging station. Charging station is there, and charging station there is a one CPU. CPU is charging point operator, which operate this charging station, and after that you have DISCOM. DISCOM is there. Distributor companies are there, which give this power to CPU for charging, giving the power to this EV. Okay, so charging station is such that it can be of three types, that is the public, private, and you have a semi-public. Okay, and also that when you are connecting this EV to this charging station, you need certain electric vehicle supply equipment charge for sending the power from the charging station to the EV. So this EV supply equipment must communicate with this EV. Okay, so and after communication it check the SOC level and how much power it can directly feed, because there are certain limits also, that is the SOC max, SOC min, and the P max, P min, how much power to be injected inside of this vehicle. So that communication is done through this certain communication protocols. And one more thing is that, and based upon that, these pins are there. One is for charging purposes and other two are for and three for communication. One more communication is there, that is the proximity control. Proximity control is such that when EV is connected to this EVSC, electric vehicle supply, through the EVSC to this charging station, so when the EV is plugged to this charging station for the charging the vehicle, so proximity control sense the EV. Since the EV says that the connector is connected properly or not. If the connector connected properly, then it will start this proximity control signal is switched on, and after that only you can give this power to the EVSC. What happens that, suppose EV is being plugged, this EVSC is being plugged inside of this EV, but the vehicle is itself moving. That is a hazardous condition for this electric vehicle and the EVSC also. In that situation, this EVSC will not give this power to this EV. Only it will check that the EV is in idle condition, it is idle condition, and the charger is properly connected. So that is a kind of control, and the same pins are being held here in shown in the figure itself. There are multiple ports. And if you see that the type 2 charger, that is the AC chargers is there for the less than 22 kilowatt. Okay. And CCS1 is the combined charging station which supports this type 1 and the fast DC charging also. And CHAdeMO concept is very old. CHAdeMO, when you remember, if you remember that when the Japan tsunami came, so at that time what happened is their grid infrastructure collapsed for the certain reason. So what happens that they uses this CHAdeMO charger, which have this vehicle to grid technology and the vehicle to home technology. They use that vehicle to charge, give the power to the home during that tsunami condition. So CHAdeMO is the very old, which already have this bidirectional power transfer facility. Okay. And this is the first type of this bidirectional charger, that is CHAdeMO. And mainly it actually originated from the Japan itself. And there is CCS2. CCS2 is such that it can support the EV charging through the either AC the type 2 or through the fast DC chargers also. If you see that there are two ports are there, one for the AC charger and the one for the DC charger itself. And there are multiple other types of connector, that is the CCS2 is there, which is a type 2, and the GBT connector. GBT is such that this is a Chinese company which collaborated with CHAdeMO and developed their own charger, that is the GBT charger for the DC fast charging. And CHAdeMO is a fast charger, fast DC charger, and with the bidirectional functionality. And the other is their Tesla supercharger. You don't have any much document related to this Tesla supercharger because they are not in the public domain, but other chargers are in public domain, and how their functionality also in there in the public domain. Okay, so this is a kind of Tesla supercharger are there. And coming to this architecture of this EV charging infrastructure, if you see this, there are EV and you have EVSC, EV electric vehicle supply equipment, which give this power EV to charge. And there is a communication between the EV and the EVSC, which already have told that a proximity control and other communication architecture. And through CMS is the central management system which operate in coordination with EVSC. So there are communication between the EVSC and the CMS also for checking the this how much power it should give, how much availability of the charger is there, and at which location is there, and how you are going to the bill, how you going to charge. So that actually handled by the CMS. And also you have the mobile application, that is CMS is actually through locating this charging station where is there for the billing, for the reservation and all. Okay, so each EV stakeholder you need the communication, and this is the communication links between all the EV ecosystem. If you consider that this is the EVSC, you have a charging point operator, then electric mobility supplier, then you have a discom. So if you see that between EV and EVSC, there are certain connectors which is being communicated. So when you put this charging gun inside this EV, so the connectors would also communicate through this proximity control and all. And also there are certain protocols, standards for this communication, that is the IEC 618.511, ISO 151182, and other also communication protocols between the EVSC and the CPU also, charging point operator, that is the IEC 63110 OCPP and IEC 61850-908, and also other communication protocol between the CPO and the distribution service provider, DISCOM, that is the distributor service provider, that is the IEEE 2030.5, IEC 608070, IEC 61850 for the communication between EVSC and the DSO. So there are certain communication protocols and the links between. Here I have shown this slide is not much clear, but is very important. So what I have told you, there are two types of charger, that is the onboard charger and the offboard charger. In onboard charger, the charger, this AC to DC power conversion, because the battery is DC but you are supplying the power AC. So this AC to DC conversion stage that is it happens inside of this vehicle itself. And in the outboard charger, this EVSC, electric vehicle supply equipment, have this onboard inverter or the rectifier for giving this power directly, DC power directly to this vehicle. Okay, so if you see the architecture itself, inside of this upper part is the outboard charger, and the lower portion is the onboard charger. If you see that from moving from the CPO side to this EV side, you have a protection unit inside, you have an electromagnetic interference filter, you have a rectifier, power factor correction unit, you have a DC to DC converter, and you have a relay and filter in the EV side also, and you have a protection system. And in central part you have a BMS, actual communication which happens between the EV and the EVSC, that happens through the BMS, battery management system. Okay, and it also has the certain communication features and protocol, that is the IEC 15118 and IEC 62351. So this whole equipment inside of this electric vehicle supply equipment itself. And if you see this lower portion in the where I'm dragging my mouse, this is the actually the onboard charger. Onboard charger is there. All things are there inside of this vehicle itself. That is the interconnection inverter, buck boost converter, power quality filter, and the EV connector and the EV battery. So BMS communicate with this through the control system and this controller outside, which is outside of this onboard charger. And there are certain communication between the electrical grid, distribution service provider, and other. This is the electric vehicles itself. So this is the two types of onboard and the offboard charger. Okay. So coming to this next topic, that is the actually most important, that is the smart charging concept. Smart charging concept, because the if you penetrate higher amounts of EV, you need that amounts of power to be charged and discharged based upon that. Okay, and it affects the grid. Grid in what sense? Because the peak power got increases. Suppose this is the load curve. This is the load curve with the normal operation. This is the morning peak and this is the evening peak. If you penetrate the higher amount of PV, then this peak power will further got increased. So you need a certain smart charging concept for this EV optimal EV integration. Okay. This smart charging concept that is based on the time of use pricing without automated control. Time of use means when you want to use that, when you want to this, you should not operate or charge the vehicle in the peak hours. You should charge the vehicle in the off peak hours when the burden on the this grid is less. Okay, basic control is the switch on and off control, that when to charge and when to discharge. And bidirectional control, that is the same concept, that is a V2G, V2H, V2B and V2L. And the dynamic pricing with automatic control. Dynamic pricing is such that, so there are electricity tariff are there, which depends upon the whole of, which varies based upon the day. Suppose there are morning peak and the evening peak are there, at that particular time the electricity tariff will be higher, and it is variable. And tariff is variable, and it is high when the peak hours are there, and it is low when the non-peak hours are there. So what is the concept is such that this electricity tariff, that you should charge the vehicle when the tariff is low. This will help you also for lowering the price of charging. And second, it also help the grid operator also, that this peak also get reduced. Okay, this is a concept of the dynamic pricing. This is already applicable in the most of these Nordic countries, there's Sweden and Netherlands. Okay, these concepts are varied. They predict this price in the 15-minute slots, less than or 15 minutes, greater than this 15-minute slot, that what price should be there. Okay, and this advantages of is this smart charging is such that utility distribution network operator, more hosting capacity and the faster implementation and the fewer cost. And the utility transmission system operator point of view, that it reduces the peak loads, avoid construction of the generation capacity. Why? Because the generator which is being supplying to this EV, it have a certain capacity. It can inject certain amount of current which is being utilized. But if you increase the EV penetration, this current level will increase. And this capacity, there are certain capacity that 70 to 80% till capacity you can operate. After that, the heating effects, the isolation loss kind of happens. So there are, if you increasing the EV penetration, you have to replace this transformer also for utilizing the higher number of EVs. So this is the importance of this smart charging, such that it avoid the construction of these generation capacities. Okay. And for building managers, that is the time of use tariff optimization, PV balancing optimization, demand charge management, the load balancing and reduction of the connection fee. Okay, this is a kind of advantage. And this is the list of the EV charging standards, which is used for also important for your solving the assignment of this week. That is the interface. You see that interface between this EV and the EVSC, that is the sockets and the vehicle coupler plugs. Communication, that is the V2G data links here and the physical signal within the different stakeholders. And system, that is the EV conductive charging. Conductive charging is that there are two types of conductive and wireless chargers. Wireless is two types, the inductive and the capacitive. And conductive is such that this is the actually just you have to plug the charger inside of this vehicle to charge the, and the wireless you just don't need any physical connection between the EV and the EVSC. And the battery swapping also have one standard, that is 62840. And conductive charging also have certain standard, that is the GBT and other. And IT, information technology between the communication and the IT equipment safety, that is the 60950. Okay, so I think that is more or less for the today's section. There are more content, but I will not go in the much into that. So let me take the one question which are already have the confusion to Dharni, that battery balancing question. Oh yeah, this question. So let me read this question again and make you solve this question again. Okay. Let me read the question. What is saying that there are certain voltage level of this bicycle battery pack, and each cell have a nominal voltage of 3.6 volt and the 2.5 Ah. And what is saying that if the BMS is programmed to balance the cells when the cell voltage deviate more than 0.05, means this is the voltage level. If go more than 0.05 volt, so then it will this BMS is programmed and this cell balancing operate from the average cell voltage. So what is saying that the average voltage is current scenario 3.65 volt, and they determine the voltage range within which the cell balancing would not be triggered. Okay, so in which section it will not trigger? It will not trigger when this it is between this average value and with the 0.05 deviation. It means that from the 3.65 volt to 3.7 volt. Okay, and the for the lower sections I was actually, this is not plus minus 0.45 volt deviation. This is just a plus zero point zero 0.05 volt deviation. So there are, so in for the below sections it is not being said anything. Okay, so when
Yes. Sorry, my voice is plainly
you
audible.
want, yeah,
Then I will complete the task.
your voice is not clear, Dilip. You can write in the chat box. Meanwhile, I will see your question. This is it from 3.65 volt to 3.7 volt. So what are options coming into this picture, that the 3.6 to 3.65, that is actually because the lower section less than 3.65 it is not being told. So this option can also come into picture, and from 3.6 to 3.7 it also come into picture because the above 3.7 volt it will operate. Okay, so also the this option is wrong, and C option can also take place because the lower section is below this 3.65 volt it is not mentioned. This is a problem in the question itself. Okay, so the question, one more question is there, that is the how EV is developing now, and I mean the what approximate in India or in the world, how far we are good going to meet the stability at the grid in real scenario. Because if we need to charge the EV at a peak hour, there will be stability issue. That is true. In our lab, what we are doing this smart charging, smart charging of this vehicle for maintaining this grid stability. Also, research is going on, and we also wanted to utilize this V2H concept for reducing the impact on this grid. Okay, so the if you see the Indian scenario, there are nearly 5 to 7% penetration is there, not much, of the EV. From the overall EV infrastructure, electric EV vehicle, if you see in the present scenario in India, only 5 to 7% are there in the electric vehicles. But in the global scenario, the rapid but rapid scenarios are there, rapid growth are there, rapid charging infrastructure installation is there. Problem in India is the space for placing this charger because the infrastructure uh, constraint is more in the Indian scenario. For that, you need land, you need a space, and you for suppose you want to charge the 5 vehicles at a time, you need the space for placing the 5 vehicles at a time. And after that, if you create a space for the 10 chargers at a time, then for that you need higher amount of space. So space is one of the constraints. Second is the policy. There is so no such EV policy that how much power you should charge at a particular time. There are not such policies are there. Their policy recommendations are there, but not practically implemented. And each state in India have its own EV policy. If you see that Maharashtra, it have a separate EV policy. If you see Punjab, they have a separate, Chandigarh have a separate, and Karnataka have a separate EV policy. So based upon that, they are maintaining their power levels, charging infrastructure, and based upon that. So research wise, it is very from the research point of view, it is a very booming topic, and you can also try that. And also, if it is below 3.6, that is fine. You can try this question, and we take you in the further tutorial session that what is wrong with this question. So this is a very growing topic, and if you wanted to do any research and take an as of PhD in that field,